Good morning, everyone. Welcome to day 5 of our research. Today's first talk is on fair division by Dr. Rohit Vaish. He is currently at IIT Delhi. So we have four talks, and one suspension talk on fair analysis.
Thank you, Pallavi. Thank you all for being here. First of all, let me also thank the organizing team for the invitation. This is my first trip to IIT Jodhpur, and I'm very happy to be here. I will be talking about fair division today and tomorrow in a bunch of lectures. And for this lecture, I'm going to talk about a specific problem in fair division called cake cutting. Before I begin, let me just mention that whatever material you're going to see here, it's all available on my website. So if you want to follow along, you can find the slides over there. Okay. All right. So what is fair division? Well, it's basically the science of dividing a set of resources fairly or impartially among a bunch of agents. And typically, these agents have preferences over these resources. Okay. So I'm going to give you a bunch of examples of settings where fair division shows up in real life. But before that, I want to hear from you. Like, what are some of the scenarios in your daily lives that you have encountered where you felt the need to divide something fairly among a bunch of people? Okay. Just want to get some sense of what you think could be potential applications of the idea of fair division. Anyone? Sorry, yeah? Yes, the classical open problem. Okay, how do you divide, some food items like chocolates among siblings? Okay, yeah. Any others? Yes. Pardon me? Uh-huh. Yes, yes. Excellent example. Yes. Yeah, yeah. So yeah, seats are your resources in your example, and what is a fair allocation of seats, right? Who should get the window seat? Who should be pushed to the aisle? You know, who should be in the better compartment? All those things, right? And there are various factors that influence it. Maybe the age of the person, or the gender of the person, or the physical condition of the person, and so on, right? Or maybe who's willing to shell out more money, for all we know, right? Okay. So yes, other examples. Time. Okay. Any specific application? Exactly. Exactly. Right. I mean, there's obviously some logistical constraints that you have to satisfy, right? Bigger courses should get bigger rooms, but among courses of roughly equal size, which should get a better room and which one shouldn't, right? So there could be all sorts of considerations. So, yeah. Yes, no, no, that is a very, very good example, and that's going to be the motivation for one of my lectures. So I'm so glad you mentioned it. So, how do you divide household chores, right? Who does the cooking? Who cleans the dishes? Who does the gardening? Right? These are very important problems, and we will talk about some of those in one of the upcoming lectures. Yes. Like differing preferences, right? Differing perspectives on the resources or preferences. Yes. So preferences are going to be absolutely, absolutely crucial for us, as hopefully you will observe in a few minutes. And that essentially determines what even fair means, right? Depending on people's preferences, you have to satisfy everyone, and that's going to govern what fair even means. Okay, cool. So lots of good examples. Let me also share some of examples that I think are relevant here. So one example could be that of land, right? Imagine there's a piece of land and there's a bunch of competing parties, right? And you have to somehow chop up the land and divide it among those competing parties. Now, because these competing agents, they have preferences over the land, right? Maybe say some part of the land is good for agriculture, other is good for mining. So if I'm looking for agricultural piece of land, I'll prefer the one that is good for agriculture and may not have too much value for the mining part, right? If you are looking to mine stuff, you might prefer the mining bit over the agricultural bit, and so on. Right? So people can have complicated preferences over the resource, and that's why it's not enough to simply evenly divide the resource into n number of parts and give it to the people. Right? Because their preferences, you have to satisfy them. You have to take their preferences into account. Okay. Okay. Here's another example. Suppose there is a shared science facility like the James Webb Space Telescope, right? And many research labs may have preferences over how they want to use it. Right? And again, you have to fairly divide the usage time among these various research labs. Yeah. Uh, Another example, as people have already observed here, is that of division of money. Right. To say you are the government and you have to divide your budget or your money among various departments or ministries. How do you do that fairly? Right. Or I'm sure, as many of us would have experienced, how do you fairly divide shared taxi cab rides? Right? Is it based on the distance traveled? Is it based on the time you spend or some other factors? Like what is fair in this case? So all of these examples, they are known as what is called divisible resources, right? So land or time or money. Why? Because we can fractionally allocate these resources, right? We can allocate them in any fractional amount as we want. This is in contrast with something called indivisible or discrete resources, where the resource consists of discrete chunks, and every chunk must completely go to one person or another. You cannot split it up. You cannot cut up in a fractional way individual resources. Okay. For example, imagine there are items in an inheritance, right? Say there's a house, there's a car, a very expensive painting, right? And each object must completely go to one person or another. You cannot cut up a car into three pieces, right, and give it to three different people. That's not going to work, right? Likewise, as someone observed, how do you allocate seats in courses at universities? Right. So Jodhpur has to decide. Okay, it has to allocate the seats in courses among various batches. So first year students, second year students, and so on. But it does not want to give all the best courses to just CS students and deprive the mechanical engineers of the good courses. Right. It has to be fair across departments as well. Right. Uh, Another example is that of allocation of public housing units. Right. You want a certain level of diversity or cultural mix in public housing. You don't want people of just one ethnic group to be clustered in one public housing facility. Yes. Because the resource you're dividing here is money, right? So, okay, up to a rupee, it's divisible. Okay, yeah, good. Uh, and another example that I think that we have very painfully realized over the last couple of years or so is that of allocation of scarce medical resources like vaccines or PPE kits. Right? How do you fairly allocate them among various sections of the population? Right? So, so these are like two basically distinct categories of fair division problems, one with divisible resources, other with indivisible. And I'm going to talk about both of these in the coming lectures, but for this particular lecture, I'm going to focus on resources of this type, the ones that you can allocate fractionally, okay? Divisible resources. Okay. And a specific problem in divisible resource allocation that I'm going to talk about is called cake cutting. And the problem is exactly as the name suggests. Okay, so you have a divisible resource, a cake. Okay, and you have a bunch of interested agents, kids, right, who have preferences over this cake. Okay, so some kid might like chocolate part better, some other kid might like the strawberry part better, some other kid might like the icing, and so on. Now, obviously, every kid wants the entire cake, right? But you can't divide the cake that way. So how do you fairly divide the cake among these kids? Right? How do you satisfy each kid based on their preference? Right? That's basically the idea of this problem. Okay? So it's a problem of fairly dividing a divisible resource because you can cut up the cake in any way you want. And it is also a heterogeneous resource because because different parts, like equal amounts of the cake, can have different values for any agent, right? So if you give me like this much from the chocolate part and this much from the strawberry part, I might value them differently, right? This is in contrast with something like money, right? So imagine there's a stack of 10 rupee notes. Okay. Now, whether I give you 5 notes from the top or 5 notes from the bottom, it doesn't matter. They both have value of 50 rupees for you, right? But there could be resources where what part of the resource you get matters. Okay, you have different preferences over different parts. And of course, different agents can have different preferences. So my preferences could be very, very different from, say, Pallavi's preferences, right? And her preferences might be very, very different from, say, Saket's preferences, and so on. Okay? So these are some of the essential features of the cake cutting problem, and we are going to define all of these things formally. Okay? By the way, please feel free to ask questions at any point, okay? All right. Okay. So here is a model to help us get started in thinking about the cake cutting problem. So the cake for us is basically this 0, 1 interval. Okay, it's a much more boring resource, but let's go with it. Okay, so this is the resource that we want to allocate, and we want to allocate this among n agents. Okay, I'm going to call a piece of cake just a finite union of disjoint subintervals of this 0, 1 interval. Okay, so anything that contains finitely many disjoint intervals is what I'm going to call a piece. And what we are looking for is a partition of this resource among the agents. Okay, so suppose you have 3 agents, yellow, blue, and orange, right? You want to divide this 0, 1 interval into the yellow piece, blue piece, and the orange piece, so that pieces of different color don't overlap, right? And you end up using the entire cake, so you don't waste cake, right? Wasting cake is bad, so we don't want to do that. Okay, all right, good. Any questions? Okay, cool. So I've been making a big deal about preferences of agents, right? So how do we formalize the preferences? Well, here's one way to do it. So for any agent I, I'm going to denote its preference with the help of something called the valuation function v sub I. Okay, and this function is going to map every piece of the cake to a non-negative number. Okay, so with every piece, this function attaches a value, a non-negative value, like how much the agent values that piece. Okay, that's the valuation function. So it's pretty abstract at the moment, but we are going to make some assumptions. We are going to assume that valuation functions satisfy certain natural properties. Okay, one natural property is that of additivity. Okay, which just says that, okay, if I give you a piece containing of these 2 disjoint intervals, right, that you individually value at alpha and beta, then your value for the entire piece consisting of the union of these 2 intervals is alpha plus beta. Okay, so your value adds up across disjoint subinterval. Okay, fairly natural assumption. Another assumption that we are going to make is called divisibility. Okay, which says that, okay, suppose you're given any interval that you value at alpha, okay, and you're given any fraction lambda between 0 and 1, then you should be able to carve out a smaller piece from this of value lambda times alpha. Okay, so whenever you have a value alpha for an interval, you can also come up with a piece with a smaller value. Like for any lambda, you can come up with a piece of that value. Okay. You can also think of this assumption as a no point masses condition. Right? There is no single point where your preferences are concentrated. In other words, your value function is somewhat spread out. It's sort of smooth or continuous in some sense. Okay. And this is, yeah. Yeah, it could be anywhere, but suffices to consider it from the start for our purpose today. Yeah, but in general, yes, you're absolutely right. Yeah. So this is for any lambda. You give me a lambda, and I'll give you a smaller piece of value that fraction times the total value. So any sort of any smaller value can also be realized. Yeah, exactly. Yeah, it's just saying there is an interval that is of value lambda alpha. Correct. Yeah. I mean, in terms of my picture, yes, but in general, you can think of it as a union of intervals as well. Yes, it could be a piece. It doesn't have to be an interval. Yes, correct. Good point. Okay, so in essence, this condition is what makes a cake a cake, right? This is what makes it divisible. Okay, all right. And the third assumption is not very crucial, but it helps me keep my slides clean, is that of normalization. Okay, so for any agent I, the value of the entire cake, the value of this entire 0, 1 interval is we are going to assume that it's 1. Okay, so for me, the entire cake is 1. For Sushmita, the entire cake is 1. For each one of you, the entire cake is of value 1. Okay, that's going to be our assumption. Right? Questions? Yes. Yeah, so any piece is a disjoint union, and this condition applies to any piece, but for now it suffices to think of X as just one interval. That's going to be enough for this talk. So allocation is anything like this. Yeah, so what you want to come up with is a partition of the 0, 1 interval into pieces. So these three together constitute a blue piece. These two are yellow piece, and this is orange piece. And you want that pieces should not overlap. So the same part of cake should not go to multiple people, right? And you end up using the entire 0, 1. There's no wastage. Yeah. Yeah. So VI. I mean, VI is a very abstract quantity. We are going to only focus on those VIs which satisfy 1, 2, and 3 properties. And if you want a concrete example, so again, this might still be quite abstract. If you want a concrete example, think of the analogy with probability density functions and the cumulative distribution functions that you may have studied in your probability courses, right? So you can think of a value function being induced by the integral of some function, okay, by induced by integral of this, and so that the value for different intervals is simply the area under the curve. Okay, any function of this form is going to satisfy the three properties I showed you before: additivity and divisibility and normalization. Okay, so these are just, if you just want some example in your head, you can think of this picture, right? But those three properties are really what we're going to use about the valuation function. Okay. Yes. Sorry, can you speak up a little bit? Yeah, so suppose I am agent I. For any piece X, right, for any combination of intervals, I'm going to assign a number, right? So my preference function maps any union of intervals to a number, and my complete preference is specified by mapping every possible piece to a number. It's a very complicated object, right? There could be uncountably many things in the domain of this function. It's a very, very complex object in general, right? And the numbers that I assign could be very, very different from the numbers that you assign. The only condition I'm asking is that your value for the complete thing is 1 and the 2 other conditions are satisfied. But other than that, you can assign numbers any which way you want. It's a complex object. It's a very, very like huge object. It has very complex description and so on. Okay. Yes. Could be. Could be. Why not? I mean, I could have an identical twin whose preferences are exactly the same as mine. That's also permitted, right? But we are not going to assume that people are the same. We want to design procedures that apply to any kind of preferences, no matter how different they are. If people are saying, okay, but I'm not going to make that assumption. Okay? I want to be as general as possible. Okay. More questions? Okay, cool. Okay, so what is fair, right? So fairness, like I mentioned, is a property of the allocation or the division, and an allocation is basically a partitioning of this form. Okay, and I mean fairness is a very subjective issue. Like different people could think about fairness differently, but as mathematicians, we love our definitions, right? So we want to pin down a definition, and one definition of fairness that I hope you find somewhat natural is that of proportionality. Okay, so I'm going to call an allocation A. So these AIs are the pieces that different agent gets, A1, A2 up to AN. Okay. I'm going to call an allocation A to be fair in the sense of being proportional. If every agent's value, if agent I's value for its own piece AI is at least 1 over n. Suppose there are n agents. Okay. So if there are 3 agents and every agent is getting a value of at least 1/3, then that is a fair allocation in this sense. Okay, and remember, this is 1/3 of their value for the entire cake, right? Entire cake is valued at 1, right? So this is 1/3 of that, or 1/nth of that. Yeah. So I mean, if it is equal to 1/n, then if you give someone more value, it may not satisfy your definition. That's why you want to say that anytime you cross that threshold, you are happy. It is possible, yes. If our preferences are completely disjoint, right? I only like the left part of the cake, you only like the right part of the cake. Great. Give me the left part, take the right part, and we are both happy. That is the golden scenario. Unlikely to happen in general, but yes. Uh, so what is yeah, good, thanks. So what we are asking for is for any fixed agent I, the value of everything is 1. It's not saying that my value for my piece plus your value for your piece is 1. We're not saying that, right? This is from a fixed agent I's perspective. Okay, good.
So in your example, the left part and right part, it's like your valuation for the right part is 0, and the left part is entirely 1.
Yes.
And my valuation for the left part is that's
Right. Yeah. But yes, but my value for my piece could be 1. Your value for your piece could also be 1. So our respective values don't add up to 1. So all that could happen, but from my perspective, the whole cake adds up to 1. Okay. Good. All right. Okay. So this is one way of formalizing fairness. Um, so here's a question for you. Okay. Is this a fair allocation in this sense? And let me tell you how to read this. So again, there are 3 agents, yellow, blue, and orange. And yellow agent's value for its own piece, the yellow piece is 0.34. Blue agent's value for its own piece, the blue piece is 1. And the orange agent's value for its own piece is 0.7. Okay, so is it a proportional allocation or not? Yes. Who thinks it's not proportional? Yeah. So these are, remember, these numbers are from different agents' perspectives. Yeah. Uh-huh. Yeah, if I am the yellow agent, this 0.34 is my value for these two together. Yes. Yes. Yeah, everyone happy that this is a proportional division? Yes? No, no, it is a definition. I'm not saying it is the definition. Yeah. This is at least 1 over n. Uh-huh. Because suppose all n agents are the same, okay? Then it makes sense to give everyone 1 over n, right? That's, we will see that in a moment, yes, right? But the definition does not tell you whether it's always achievable or not, but we will talk about that in just a few slides. Yeah, good point. In some sense, yeah, but I mean, it's the idea that okay, if there are n people around, I should at least get my proportional share of the entire cake, right? Exactly, exactly. At least imagine the edge case where there are n copies of me, right? So then every one of us should get 1 over n value, right? And this is sort of extrapolating that to the non-identical case, right? Now, I mean, just by looking at the definition, it's not obvious whether you can always achieve such a division, but we will see. We'll come to that in a moment. Yes. No, it is so. Yeah, so normalization said that yellow agent's value for yellow piece and yellow agent's value for blue piece and yellow agent's value for orange piece should be 1. The numbers you're looking at are not just yellow agent's values. This is yellow agent's value for its piece and blue's value for the blue piece and orange agent's value for the orange piece. Yeah, yeah. So yeah, so yeah. From if all the numbers were from the yellow agent's perspective, then they would add up to 1. But these are not all from yellow agent's perspective. Okay. Yes. Exactly, exactly. So blue's entire value is concentrated in these pieces that it is getting, and it doesn't really care about the yellow and the orange piece. Exactly, good point. Yeah. Okay. Um, good. Any more questions? Okay, cool. Right. So this is a proportional allocation. I hope we all agree with that. Okay. Uh, for the same reason, this is not a proportional allocation because the yellow agent is slightly below the threshold of 1 over n. Okay. All right. Cool. So someone said that like why is yeah yes. Yes, yes, excellent. And this is exactly why we need a definition like this. So we have I'm going to talk about a different fairness notion, and hopefully that will address the point that you are trying to make. Okay. Um, so there's another way in which we can formalize fairness. Okay, it's called envy freeness. Okay, and this is a condition that applies to pairs of agents. So for any pair of agents I and j, right? Say me and you. Okay. Say I am agent I. Okay. Then my value for what I got, Vi of AI, should be at least my value for what you got. Okay. So I should be at least as happy with what I got, and I should not envy you. I should not have a higher value for what you got. In other words, I don't want to switch with you. Okay. And if this condition holds for every pair of agents, then we say that the allocation A is envy free. Okay. So no agent wants to switch with any other agent. Everyone is happy with what they got. Good. All right. Um, so here's an allocation. Okay. Yes. Right. Mhm. Exactly. Exactly. So the index is quite important, right? And this condition holds for every INJ. Um, Okay, so maybe I should have phrased it differently. I should have said I should not have a preferential, I should not strictly prefer someone else's piece. Okay, so it's not actually a swap that is happening. It's the desire to swap from some agent's perspective, and that there should not be any desire to swap with anyone else. Okay, I hope the definition is clear to everybody. Okay, okay. So here is an allocation. Okay, again, three agents, yellow, blue, and orange. But now all numbers are from just blue agent's perspective. Okay, so this is blue's value for blue piece, blue's value for yellow piece, and blue's value for orange piece. And note that they all sum up to 1. Okay, they should because of normalization. Okay, my question for you is it an envy-free division? Why? Someone raise your hand. Yes. Exactly, right? So if I'm the blue agent, I have a value of zero point 0.4 for what I have. But if you're the orange agent, I want your piece, right? Your piece is of higher value for me. So I would like to, I would rather have your piece than mine, right? Okay, cool. And so this is not an envy-free allocation, okay? Because I have a desire to switch with you, okay? Cool, all right. So these are the two notions of fairness, proportionality and envy-freeness that we are going to be talking about today, okay? But just as a sort of a warm-up exercise, I want to understand which of these notions is stronger, okay? Is it the case that an allocation satisfying one of these definitions implies the other? Or could it be that these are incomparable, meaning an allocation satisfy one without satisfying the other? Okay, so let's start with a very, very simple setting of just two agents, just two people, n equals to 2. Okay, and my question is one property stronger than the other? In other words, if you have a proportional division between two people, is it envy-free? If you have an envy-free division between two people, is it proportional? Or none of those things have to be true in general? Why? Mm-hmm. You're using normalization, or are you using? Right, right. So if I am agent I, and I only have two pieces in front of me. One is my own, the other is agent J's piece. Right. These two things sum up to exactly 1, and my piece is at least as good as the other, so it better be a value of at least half. Okay. But as soon as it's a value of at least half, my proportionality threshold has been reached. Right. By the same argument, agent J's proportionality is also reached for its piece. Right? Because J does not envy me either. Good. So envy-free implies proportional for two agents. Yes. What about the converse? Yes. Yeah. Why? Yeah, yeah. Why does left imply right? Exactly, exactly. So if I'm agent I, proportionality says I'm getting a value of at least a half, which means my value for the other piece is at most a half because of normalization. That means I don't envy the other person, right? And likewise, the other person does not envy me. So that's why this is an envy-free division, right? So for two agents, these are the same properties, right? Any allocation satisfying one definition implies the other. Okay, very good. What about more agents? So suppose you have three agents. Is it still the case that they are the same properties, or is one stronger, or are they incomparable? Maybe raise your hands. Um, yeah, go ahead. Mhm. Possibly, possibly. It's still proportional from your perspective, but you have a significant envy. Good. So proportional may not be envy free, right? And in fact, I claim that you have actually seen such an example uh, like this one, right? So this was proportional from the blue agent's perspective because it was above zero point 0.3, right? Certainly, it was not envy free. Okay, so there could be situations where an allocation is proportional but not envy free. Okay, what about the converse? Sorry, who said? True. Why? Who said? Oh, you said true. Okay, yeah. Exactly, exactly. So it is a very simple exercise, right? You just write up all the n inequalities from agent i's perspective, add them up, right? So because it holds inequality by inequality, it should also hold an average, and that gives you proportionality. Okay. So if you don't see it immediately, just try it in the coffee break or something. It's a pretty straightforward exercise. Okay. But for now, just believe me that NV freeness implies proportionality for any n, any number of agents, meaning this is a strictly stronger property. Okay, strictly more demanding notion of fairness. Okay, and the converse holds only up to 2 agents, but not for more agents. Yeah, good. All right, cool. So these are the two fairness notions that we are going to be playing around with. Okay, all right, cool. So we might want to now design algorithms that find either proportional or NV-free divisions, right? Uh, but in order to argue about the complexity of this algorithm, right? So we like to say that we want to design a polynomial time algorithm, right? And that polynomial is a polynomial in the input size, right? So what is the input size here? Exactly, the input is very complicated, right? It's a valuation function, right? And its domain is massive, right? So if we say it's polynomial in the size of the valuation function, that's not a very meaningful guarantee. Right? So we want to define some way of accessing this input, some way of talking to the input, and that's precisely the Robertson web query model. Okay, so we are not going to write the input down completely. We are just going to access it by means of questions or queries. Okay, and we are going to allow ourselves two kinds of queries. One is called the evaluate or eval query, and the other is called the cut query. Okay, these are both ways of accessing the valuation information. For the eval query, so both are indexed by I for agent I. For eval query, we are given 2 points, x and y. And so if we give as input to this oracle the points x and y, the oracle responds back by saying, okay, this is agent i's value for the stuff enclosed between points x and y. Okay, so pictorially, I give as input x and y, and I get as answer the value alpha that agent I has for this bit here. Okay, that's the answer of the eval query. Yes, yeah, exactly. Yeah. We ask Oracle, okay, for agent number 17, if I give you points x and y, how much does it value the piece? And it tells us the value. Okay, this is one operation that we're going to allow our algorithms to do. The other operation that we're going to allow is the cut operation. So this is sort of the opposite of that. So this time we are given a point x and a number alpha. And the Oracle is going to tell us, okay, for what y is the enclosed value equal to alpha? Okay. Okay. So cut query is going to return a y given as input an x and an alpha. Yes. Yes, yeah, exactly. It won't matter what y you return, but if you want to fix a convention, let's say you get the leftmost y. Yes. It has to be exactly equal to alpha, yes. So if it spikes, it's not divisible. So you don't have point masses. So it can't be too spiky. Yeah. Then you just return some null or something like that. Yeah. Yeah. So I mean, you could in principle issue alpha equals to 20, but because of normalization, there is no such y, right? So then the oracle will say there is no such y. Yeah, so either there is a y in which you get one of the feasible answers. If there's no such y, you get a null or no response or whatever. Yeah. There was a question. Yeah. No. Yes. So this is just for agent I, right? So we have fixed agent I, right? We are only interested in agent I's preference for this query. You could ask the same question for different agents. That's fine, but this specific query is only for agent I. Okay. Yes. Yes, yeah. So we are going to assume that these are constant or like unit time operations for our algorithms, right? And when we say it's a polynomial time algorithm, it's basically a polynomial query algorithm. So it makes a polynomial number of such eval and cut queries. Okay, this is the unit of complexity of our algorithms. Okay, yeah, good point. Thanks. Okay, any other questions? All right. So let's get into algorithms. Okay, let's start by designing procedures that find fair solutions. Okay, and let's start with the simple setting of just two agents. Okay, and let's start with the weaker notion of the two, proportionality. Okay, a very very simple setting. So how do we find a proportional division between two agents, no matter what their preferences are? Okay, so this is a pretty natural strategy. It's called the cut and choose strategy. Okay, I'm sure you all must have heard about it or come across it in some form or the other. And here's how it works. Okay, just two agents. So agent one is going to come up first. It's going to cut the cake into, it's going to make a cut, and it's going to divide the cake into two pieces that are both equal in value, that are both of value half. Okay, we can do that. It's a cake, right? And now we invite agent two, right? And ask agent two, okay, according to your preferences given by V2, which piece do you like better? Right? Maybe agent two says, I like the right piece better. So we are going to give the right piece to agent two, and agent one is left with the left piece. Okay, simple enough, right? Yeah, okay. So is this a proportional division? Why? Anyone? Yeah, exactly. So because the second agent, the blue agent, is going to pick its preferred piece. It picks a piece of value at least a half. And the other agent created an equal cut according to its own value. So it gets a value of exactly a half. Right? So both are getting greater than equal to half for their respective pieces. Yes. So yeah, yeah. I mean, doesn't matter what the values are, but you just make a single cut, and you can always make this cut because of the divisibility condition. So no matter whether you value the corner pieces a lot and you don't value the stuff in the middle, your cut would be accordingly positioned. Right? So suppose I'm agent one and all of my value for the cake is concentrated in this bit here. Then the cut that I'm going to make is also going to be sort of around the halfway mark over here. Right? I mean, in this picture, oh, I'm so sorry. Okay, right? Right? Does that make sense? So whatever your value function is, you make a cut according to that. It doesn't have to be exactly between 0 and 1. It could be anywhere depending on your preferences. Okay? Okay? Okay, so this is a proportional division because 2 is getting a value at least half, 1 is getting a value of exactly half. Is this NV free as well? Why? Same properties, right? Proportionality and NV free are the same properties for two agents. So we get NV freeness for free. We don't have to work at all. Okay, cool. So can we do all this in the query model that we just saw? The Robertson web query model with the cut and eval queries. Can we do that? Okay, so what would be the XY? What would be the XY in the, yeah. 0, 1/2, okay. You just basically have to evaluate one of the pieces because you know that they add up to 1. So you just need one evaluate query. Excellent, good, right? So you can just run one cut query from agent one's perspective and do an evaluate of just one of the pieces from agent two's perspective and then make a decision which piece is better. Okay, so good. So we have our first theorem that for two agents, an NV-free, i.e. a proportional cake division, can be achieved using just two Robertson web queries. Right? In other words, this is a constant time algorithm, so to say. Okay, good. Any questions? All right. Yeah. Mhm.
Can there be a third definition where that the requirement is VI of AI is same across?
Yeah, good. So I think what you are hinting at is a different fairness notion. It's called equitability. And I mean, it has a name, and the condition is precisely what you're saying. So for any pair of agents I and j, what you're asking for is agent i's value for its own piece ai is exactly equal to agent j's value for its own piece, right? So if I get a value of 0.7 from my piece, then Sushmita should get a value of 0.7 from her piece, and Pallavi should get a value of 0.7 from her piece, and so on. Okay, so this is known as an equitable division. Um, I won't be talking about it, but you should ask me about it over the coffee break or something. Okay, it's a well-studied fairness notion, and again, you could do all this algorithmic work for that notion as well. Okay, all right, but yeah, but this has a proper name. Yeah, good point. Okay, cool. So this was for two agents. Okay, let's move to a more general setting with arbitrary number of agents, any n. Okay, now we want to find a proportional division for any number of agents. Any thoughts how to do it? So everyone should get at least 1 over n. Okay. Make a cut and mhm. Who has the maximum value for? Okay. Okay.
That piece value to be greater than 1 by n, give it to them.
Okay.
That no one has, kill it.
Okay. So then you should tell me what you'll do in this case. So this is the cake. This is 0 and this is 1. Okay. So you said that let's pick some agent, agent 1, and make a mark so that this bit here is 1 over n. Okay. Now say I'm not agent 1, I'm agent 2. Okay. And is also agent, Sushmita is agent 3. Okay, cool. And for both of us, the entire value of the cake is here. Okay, both of us. Okay, now you're saying that, oh, let's give it to the agent who values this the highest. So say you chose Sushmita, right? So she's very happy, right? But I'm devastated, right? So this won't be proportional for me. It doesn't matter what you do with the rest of the cake, right? So excellent, yes. Yeah, so we'll use a similar intuition, but we'll look for the leftmost mark where your proportionality threshold is reached. Okay, okay, good, right? So, oh, good, right? So there's a lot of text here. You can ignore that. But imagine a moving knife procedure, okay, a continuous procedure where I take a knife and I move it from left to right gradually, okay? And as soon as any agent's value for the left bit hits 1 over n, they should shout stop. And I pause there, right? So suppose I move the knife and, say yellow agents, so there are 3 agents, suppose, okay? Yellow agent's value reaches 1/3, it shouts stop, right? I pause here, I give the enclosed bit to the yellow agent, and I kick it out, okay? And I repeat the process. So again, I start moving. Now there are 2 people left. Again, I start moving. As soon as somebody's value for the enclosed bit hits 1 over 3, they shout stop, right? And again, I give that piece to that agent and kick it out. And the remaining agent gets the leftover piece. Okay, you can imagine doing this for any n. I've shown it for 3. Okay. Then pick anyone you like. Doesn't matter. Um, you can say that because okay. So let's try to argue that. Okay. So why is this proportional? Okay. So every agent who gets a piece is getting exactly 1 over n by virtue of shouting, right? Any agent who did not get a piece is having a value of at most 1 over n taken away from them, right? So they still have a lot of value left in the remaining cake, right? So even if two people shout at the same time, one of them is going to get the 1 over n value, the other is going to lose at most 1 over n value. And they still have a lot of value left in whatever is left in the cake, right? Whatever cake is left. Okay, so that's why this procedure always gives, and you can imagine that the last agent gets at least 1 over n, right? They might get way more than 1 over n for all we know, but definitely they get 1 over n. Mhm. Okay, you'll have to call out the example again. Sorry, yeah. So 3 people, right? Okay, now what? No, no. So if there are 3 people, everyone has to shout when their 1/3 value is reached. No, no, exactly 1/3. So you shout when your value is 1 over n, exactly 1 over n, not at least 1 over n. As soon as it reaches 1 over n, you raise your hand, right? So I think that's important. You don't want to wait. The knife would have passed your preference point and you might be left with nothing, right? So as soon as it reaches 1 over n, you raise your hand. Mhm. Say, okay. So right at that point, if I'm person 2, what you have taken away is of value 1 over n to me. So how much value do I have left in the system? It's 1 minus 1 over n. And there are n minus 1 agents left. So you can repeat. Excellent, excellent, good. So you are preempting my slides. Okay. So can you run this gradual continuous procedure in a discrete way? I claim yes. Exactly, exactly. So what you do is uh, you just ask every agent a cut query of value 1 over n, right? You get n answers, you line them up, and you take the leftmost one, right? Smallest y, exactly, right? And then you have n minus 1 agents, again ask them for 1 over n, and lather, rinse, repeat. Okay, cool. So again, easy to observe that this takes quadratic number of queries. Okay, all right. Yes, good, good, good. So whatever I'm talking about here, it assumes that people are all nice and truthful, right? They tell you what they believe, right? But they don't have to, right? So that is a sort of a game theoretic angle on the whole problem, right? If people are allowed to misreport their preferences, what are they going to tell you, right? And imagine, I mean, this is easy to see even in the cut and choose protocol, right? The cut and choose protocol asks me to make a cut point at half according to my value. But if I know that the second agent's value is concentrated way to the right, I'm going to push that halfway mark, right? I know that the second agent is going to pick the right piece nevertheless, but I managed to salvage a value of more than half for myself, right? So people can certainly game these algorithms, right? And again, I can tell you more stories about it over coffee break. Okay, so this is again a very well studied set of questions. Yes, yes. If you know the preferences, you can definitely give. Absolutely, and then you start talking about Nash equilibria and cake cutting, and it becomes a very very interesting problem. So yeah, uh, but yeah, for now let's just keep things simple. Let's assume that people tell you the truth. Okay, I think the problem is very interesting even with truthful people. Yeah, yeah. Okay, cool. All right. Good. So here is the story of this proportionality notion. Okay, we can tell this story along this axis of query complexity, right? Just to summarize what we know about this fairness notion. So at the lowest rung of this ladder, we have the two agent case, the cut and choose protocol, which gives proportional divisions for with just two queries. Yeah, and we have seen that there is an upper bound. So for any n, you can find a proportional division using n squared number of queries, right? Okay. But now you might ask, well, is n squared the best we can do, or is it possible to do better in terms of query complexity? Okay. And turns out you can do better, right? So there are protocols that take only n log n many queries. Um, this is again a very nice exercise. Try to come up with protocols that take n log n queries on your own. The hint is that it uses recursion. Okay, so I'm not going to say more, but try to work things out. Okay. Interestingly, this is tight. So there exist instances of cake cutting problem where any proportional division algorithm will take n log n many queries. Okay, so n log n is the right number when it comes to proportionality. Okay, all right, cool. So this was proportionality. I want to talk about NV freeness, but I don't know, Pallavi, how much time do I left? 5 minutes? 5 is okay? Okay, cool. Okay, so let me I wanted to tell you about algorithms for NV-free division, which turn out to be much more intricate. But given the time limitation, let me just give you like the summary of what we know about the NV-freeness problem. So this was all about NV-free divisions for 3 agents. Again, these slides are up, so you can take a look and talk to me if you have any questions. But let me just skip through. All right, right? So let me just tell you the story of NV-freeness, okay, what we know about NV-freeness. So again, from the 2-agent protocol that we saw, because for 2 agents, proportionality and uniqueness are the same properties, so we get this result for free, right? Okay. For 3 agents, the algorithm that I did not talk about, I mean, there is a very clever protocol by Selfridge and Conway from the 1960s that finds an NV-free division, which remember is a stronger property than proportionality, using again a constant number of queries. Okay, but right off the bat, even for 3 agents, the problem becomes quite intricate. Like it's a very clever protocol. Okay. So this was in the 1960s, and then until mid 90s, we did not know a whole lot about cake cutting until these 2 people, Brams and Taylor, political scientists, they showed that there is a finite but unbounded protocol for NV-free division. Okay. Finite means that given any input, their procedure will terminate. Okay, it does not run forever. But unbounded means that they could not give a bound on the running time purely as a function of n. Right? So their running time depended on n as well as the VIs, the valuation functions. Right? Which meant that you could make the protocol run for as long as you want by cooking up some strange preferences. Okay. So this was one of the downsides of their otherwise very impressive result. Okay. Anyway, so this was what we came to know of in 1995. And then in 2016, a couple of computer scientists came along, and they gave what is a finite and a bounded protocol. Okay, so the running time bound depended only on n, did not depend on the VIs. But I think as you can observe, the bound wasn't particularly encouraging. Okay, so it was n to the 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 n. I mean, it still counts as a win in theoretical computer science, but okay. But yeah, it was a bounded protocol, so that was good. Okay. But I mean, you can see that even for n equals to 4, this is just going to explode, right? Yeah, exactly. Okay. So this was what we knew from 6 years ago, right? Um, it's a finite number of n's, yeah. It's just 6 n's. It, yeah, it does not depend on the VIs, only on n, and it's only 6 n's. Okay. All right. Unfortunately, the best lower bound that we know of is quadratic. Okay. So there is a massive gap in terms of the upper and lower bounds that we know for the NV-free cake cutting problem. Okay. I mean, it's as big a gap as you see in any combinatorial problem that you commonly encounter. Okay. So I think this is a fabulous open problem to work on. A challenging open problem, but I think also a very rewarding one. So this actually, yeah. So the key idea in their protocol is something that I skipped over. It's called the irrevocable advantage, which basically says that okay, so it's a recursive protocol. It divides NV-free. Comes up with an NV-free division of a partial cake, sets some of it aside, right, and then goes to that bit and then divides it in NV-free manner and then goes on and goes on. Okay, so it does it in sort of steps, and it creates something called irrevocable advantage, meaning in the first round I'm going to assign the partial cake in a way. So say Sushmita and I are the agents, right? I'm going to assign cake to Sushmita and myself in a way that even if I get any amount of the rest of the cake, right, Sushmita won't care. She still won't envy me, right? So she has a very strong preference for her own allocation from the round one, that even if I get a lot of the other stuff from the subsequent rounds, she doesn't care. So that part of the envy, so if you think of envy graph, right? If you think of it as a graph and draw edges of envy, that edge is somehow fixed. Right? This is known as irrevocable advantage, and they make use of this idea in a sort of it's basically irrevocable advantage on steroids. Okay. Um, yeah. This is power. This is a hyper exponential 6 only. Okay. All right. So in the last maybe a minute or so, I had a challenge problem for you guys. Okay, so you may or may not recognize some of these faces, but this is a variant of the cake cutting problem. Okay, on a social network. Okay, so in this network, every person is a vertex, a node, right? And they can only care about the people who are neighbors to them in that network. Right, so I can only potentially envy those who I'm directly connected with, not those who are further away. Right, so it's not like envy finesse where you check for every pair. Here you only check for every edge. So it's somewhat of a relaxed notion. Okay, so suppose there are 4 people who are connected this way, right? So for example, Pallavi is over here, right? She only cares about not envying Fahad, but doesn't care about what the other people get. Okay, and likewise for everyone else. So my challenge for you is to come up with an envy-free protocol for 4 agents on this path graph that takes a small number of queries. Okay, only 30 queries, but okay, I'm happy to relax this number. Okay, no proportionality you can get for any n using the procedure that we saw. So NV implies proportionality, right? We okay. Oh, on this exactly, right, exactly on this graph. No, exactly. Yeah, good point. Yes, thank you. Yeah. Okay. So think about it over lunch break or coffee break, and let me know. Send me an email. Here's my email. Okay. So any questions? Yes. Or any solutions? Just send me a draft. Yes. Yes. You can prove that there exists an envy-free solution always in a non-constructive manner. So without actually giving a protocol, by using something called a fixed point theorem. So if you have heard of things like Brouwer's fixed point theorem or Sperner's lemma, right, these things have application actually in game theory in proving existence of Nash equilibria. You can use those techniques to demonstrate the existence of an envy-free solution, but they are not constructive proofs, so they don't give a procedure to find such an allocation. Yeah. Uh-huh. They should not envy. So Fahad should not envy Pallavi or Sushmita, but he doesn't care what I get. Yeah, you should only control for envy along the edges, right? So Fahad could envy me. That's a fine thing, right? So it's a relaxation of the envy procedure that we saw. But now I'm going to, because it has 4 people, so it's not a very easy problem, and try to come up with something that takes a small number of queries. Not a very difficult problem, but not immediate either. Yes. Sorry. I can't hear you very well. Uh-huh. Right. It's a relaxation of the click problem, right? So if this was a 4 click, like everyone was connected to everyone, that's the standard problem. So if you find an envy-free division in that problem, it's envy-free here, obviously, right? But then that problem is hard, right? We saw that for general n, it just blows up. So I'm trying to make your life a little bit easier, by giving you a graph, but it's still a challenging notion because it's NV freeness, not just proportionality. So, yeah. Mhm. No, you still have to find envy freeness because you should not envy any of your neighbors point wise, right? It's not just the average that you have to be above. You have to independent set. Yes, yes. Then you don't like. Yeah, exactly. Then you don't care all that much, right? Yeah, you evaluate envy along the edges only, right? So yeah, exactly. Yeah, it was completely. I searched four random faces on the internet and these came up. So no, no, they are completely fictional people. They have no resemblance to living creatures. Okay, cool. Okay, let me stop here. Yeah. Okay, thank you.
Okay. Thank you, sir. So now we'll have a coffee break till 11 and we'll meet again.
फायदा नहीं था इतना दूर था
Did आवाज नहीं गया?
Okay. Were you working with this?